Welcome everyone to another session on the course Line Commutated and PWM Rectifiers. Today we will be talking about neutral point clamped NPC rectifiers. So in the course structure, we are now in this uh, week 10 here. In this week, we are going to talk about two types of rectifiers which are typically used in three-phase applications for higher powers. One is the NPC neutral point clamped rectifier, which we will talk today. And subsequently, we will talk about the VNR rectifier. VNR rectifier is something which has recently been popular, but when you analyze the rectifier, we will understand that it is an extension of NPC rectifier. More specifically, it is an extension of T-type NPC rectifiers. Okay, so and here we will talk mostly about the steady state operations. So in with regard to the neutral point clamped converter, we will talk about the circuit topology, the space vector diagram, a little bit of carrier based PWM, and midpoint voltage balancing and other topologies. So neutral point clamp converter, it is an important converter for high power applications and for three phase. So in module C, we talked mostly in single phase applications. Now we are talking more about the three phase applications, and in which this particular neutral point clamped converter is one of the most important topologies, and one must learn this one as part of the course. Now, they are used extensively in motor drives as well as in grid connected converters. Okay, in many places, in PV systems or in battery storage systems, we find that this converter is very suitable and commercially very much deployed in real life. Okay, and also as if you use this converter, this is a bidirectional converter, which means it can act as an inverter, it can act as a rectifier as well. And as rectifier, it is all many times used at the front end when there is a grid connection happening. For example, you can use NPC here, okay, and here you have your grid. Okay, you can, this is three phase, and then you can have a DC link, and then you can have another NPC. This is a back-to-back NPC, which can go to a motor drive. Okay, so this kind of structure, we have seen this one in a back-to-back voltage source converter. This is also true for a neutral point clamped converter, and this is generally used for high power applications. Now, I have another lecture which is part of the NPTEL, and where I have talked more about high power converters in this lecture series. So there is some repetition of that lecture series with what I'm going to cover today. So you can also look into this link, or you can search in the NPTEL website and can find more information about what I'm going to cover today, additional information. Okay, now this here is the circuit. So how do we get the circuit topology of the NPC? We can start with the two-level voltage source converter, which is shown here, having two switches, S1 and S2. And we can see that the output voltage here, if I take this as the reference voltage, this is 0 and VD. Okay, uh, so when we create the sine wave out of at this pole voltages, then we can see that the instantaneous voltage is always fluctuating between 0 and VD, but the sine wave is embedded inside the this instantaneous waveform. Now, if you if we can make this voltage as a three level waveform, okay, what do you mean by three levels? You can see here this instantaneous voltage which is coming here, okay, it has now, so if I take this as the reference point O, okay, and this point's voltage has plus Vd by 2, minus Vd by 2 and 0, right? Suppose you turn on S1, then you get plus Vd by 2. And if you turn on S3, then you get 0. And if you turn on S2, then you get minus Vd by 2, right? So therefore, you can see that this, by putting an additional switch S3, we can get three levels of waveform at the output voltage. Okay, why do we need such a three level waveform? Because the fact that this waveform of three levels is more or closer to sine wave as compared to the two level waveform. So you can understand here that the instantaneous error, suppose I take the instantaneous error between the actual waveform and the uh, desired waveform. So you can see here, for example, if I follow this red colored curve, okay, sinusoidal one, the instantaneous voltage is actually this one at this point, okay, whereas the desired waveform is here, okay, we are trying to make a sine wave, but the instantaneous waveform is here. On the other hand, if you see this condition, the desired waveform is the red one as before, but now the voltages is like fluctuating in the positive half cycle. It is fluctuating between 0 and Vd by 2. So the instantaneous error is less. Instantaneous error, okay, between the actual voltage and the desired voltage, this error is less in this second one as compared to this one. This instantaneous error is basically what causes the harmonics in the output waveform. If you can make the instantaneous error 0, then of course you have achieved the perfect sine wave. Okay, so if now if you compare the waveforms of the two level and the three level, you can see that in a three level converter, because there are three levels of voltages possible at the output, so the instantaneous error is less in a three level output as compared to the uh, two level output, which means that the harmonics generated will be less in a three level waveform output. Okay, so the harmonics are better, which can further uh, reduce the size of the filters that we will use at the output if we are connecting to the grid. Also, one more important is this is not for grid connected application, but for motor connected application. For lower DVDT will be amplified, because here the output voltage, the DVDT is half here as compared to the upper waveform. Okay, because in the upper waveform, the dVdt is going from 0 to Vd. The delta V is 0 to Vd, but in the lower waveform, it is only 0 to Vd by 2. So therefore, the lower waveform has also lowered dVdt, which actually helps when you put for motor applications. dVdt causes extra currents and wave reflection at the motor terminals. So therefore, this waveform is better. Okay, if you talk from the harmonic point of view, from the filter design point of view, or from the dVdt point of view. So this waveform is a three-level waveform, and a three-level neutral point clamp converter can produce this type of a waveform. So as we have seen here, okay, so here is the more detailed analysis. So if you see here this Vd by 2, if you turn on S1, then you get Vd by 2, okay, at VAO voltage. Whereas if you turn on the middle switch, then you get 0, okay. And if you turn on the lower switch, then you get minus Vd by 2, right? So this is how you will be able to get the three levels of waveforms at the pole voltage. VAO is called the pole voltage of this converter. Right. Now, if you see carefully a little bit more about the voltage rating of the switches, voltage and current rating. What is the current rating of the switches? The current rating of the switch means how much current it will conduct when it is fully turned on. So this current should be equal to the load current. Okay, if you the load current, whatever is the peak value of the load current, the switches must carry current same as that magnitude. Okay, like when this switch is conducting and this switch is conducting and this switch is conducting. Okay, of course the current will be bidirectional. Okay, so it should be able to carry current in both the directions, these switches S1, S2 and S3. So that is one thing. What about the voltage rating? Okay, now if you want to understand the voltage rating, then what you have to do is to see what is the voltage which gets applied across the switch when you turn it off. Okay, so suppose this switch is on. Okay, this switch is on. In that case, the voltage which needs to be blocked by S2, you can see here this voltage with a terminal with a positive sign here should be is getting applied across S2. So the magnitude of this voltage is equal to VD. Okay, because if you see here, if this is your reference point, not zero, suppose this is your reference point here. So then if you see when this switch is on, so this point's voltage is exactly equal to VD, right? So S2 must be blocking a voltage of magnitude VD, right? So the voltage rating of S2 must be VD. But what about S3? How much voltage it has to block? So you can see here, this point voltage is plus. So this point is plus, and therefore the voltage across S3, you can see clearly, is plus VD by 2. Okay, plus VD. So with the plus where I have shown it with the green colored plus in the in this in the slides. Okay. But on the other hand, suppose you turn on the lower switch. Okay. Okay. You turn on the lower switch and you turn off. S1 is now off. Okay. So if S1 is off and S2 is on, right, then what happens? You can see this point is now connected here. Okay. And then this point is becoming plus, and S1 has to again block a voltage of VD, right? And it will come across this switch here with the terminal shown. So S1 should also have a voltage rating equal to VD. But what about S3? Okay, what about S3? If you carefully see, since this point is connected here, now S3 has a voltage of plus here and minus here, and it has to therefore block a voltage of minus VD by 2. Earlier it was plus VD by 2 and now it is minus VD by 2. Okay, so which means that this S3 switch, okay, this S3 switch must be a switch which can carry current in both the direction, and it can block the voltage in both the direction. Magnitude of the current is IL and magnitude of the voltage is VD by 2. So therefore, this switch must be a 4-quadrant switch. S3 is a 4-quadrant switch. And this 4-quadrant switch means it can block voltage in both the directions and it can carry current in both the directions. There are many implementation of 4-quadrant switch. One of these implementations I am showing here. When we will talk about the VNR rectifier, we will see another implementation of the 4-quadrant switch. Okay, but this is one implementation. And here, this is a 4-quadrant because this diode will, so the current can flow in this direction and the current can flow in this direction when the two IGBTs are turned on. Whereas if you turn off the IGBTs, um, if you turn off the IGBTs, then uh, you can actually block voltages of both the directions, right? So therefore, S3 can be realized by this one possible circuit implementation is using an IGBT with a series diode. Other possibilities we will see later. Okay. So now, but one problem here is that these two switches, S1 and S2, have voltage rating which is double than that of S3. So in order to get rid of that problem, what we can do is we can series connect S1 and we can series connect two switches so as to kind of like make uh, um, the voltage rating of all the switches equal to VD by 2. Okay, S5 still is a 4-quadrant switch. Now, with some clever manipulation, actually we can go from here to there, okay, where we will see that uh, we can actually remove that requirement and we can like put this S5 switch in, split it in this way. Okay, why do we do that is becoming clear here, that if I put the two switches S5 and S6 here in this way, basically we can actually introduce two diodes and we do not need these two as controllable switches. Okay, and S1, S2, S3, S4 are therefore always controllable switches. Okay, and so the one phase of this converter therefore looks like this. Okay, with two diodes. These are called clamping diodes, NPC clamping diodes, and then there are four switches like this here. Okay, this is how one phase of the converter look like, and all switches have a rating of VD by 2. And this is what is the three-phase NPC looks like. Okay, here you can see this is phase A having two uh, clamping diodes. Then you have the phase B and you have phase C, which are identical. The middle point of these diodes are connected to the mid point of the DC bus. Okay, so this is how the converter looks like. Of course, you can have a load here, but you can as well have a grid here. Okay, so the grid can be present here. So this converter is basically, from the structure, it is a bidirectional converter. So power can flow both the ways, and so it can act as a rectifier or it can act as an inverter. This converter was proposed by a very famous Japanese professor, Professor Akagi. So he is from is from Tokyo Institute of Technology, and it was proposed around I do not remember exactly, but around 1982 or 83, somewhere at that point of time. Okay, so yeah, so this converter has become actually a very popular converter. It is very much is used in many countries, especially Japan. It is used very frequently. Okay, and there are variants of this converter. Okay, now let us understand a little bit about uh, the current direction. Okay, at first, if you analyze this converter, you will feel a little bit overwhelmed because there are so many switches. In fact, there are four switches along with their anti-parallel diodes, and there are two additional midpoint or clamping diodes. Okay, and so it is quite natural to get overwhelmed with this circuit initially. However, if you analyze it step by step, you will be able to get to the reason why all these switches are used. Okay, so let us take a condition where I is greater than 0. That means this current is flowing out. Okay, so this current is flowing out, so I is greater than 0, right? So which suppose we want to get Vd by 2, okay, with respect to this VAO voltage. Suppose we want to get Vd by 2, okay, at the output. So which are the switches we will turn on? Of course, we will give the gate pulses to S1 and S2, okay, and since the current is greater than 0, the two IGBTs will conduct, right? Fairly straightforward. Now suppose for the same current, which is again greater than 0, I want to get 0 voltage. Okay. In this case, what we will do is that I will remove the pulse from S1. You can see S1 has no pulses now. And I will simply turn on S2. I will give the pulse to S2, right? And so what will happen here is that the current will now flow from here and through the IGBT and going like this. So then D5 will get turned on automatically. Okay. And this is how I greater than 0 and VAO equal to 0 voltage is possible to get. Now let us take the third condition, which is I greater than 0 and VAO is minus Vd by 2, right? So in this case, since I want to get a minus voltage, what I will do here is that I will give pulses to gate pulses to S3 and S4. Okay, I will give the gate pulses there. But what will happen here is that since the current is greater than 0, so the current will flow through the antiparallel diodes of S3 and S4, which are this D3 and D4. Okay, so even if I give pulses to S3 and S4, gate pulses to S3 and S4, the IGBTs will not conduct, whereas the two antiparallel diodes D3 and D4 will conduct here. Okay, so this is the condition. What happens with I greater than 0? We can as well similarly make how the converter will operate with I less than 0. So suppose I have I less than 0 and you have this VAO equal to, I want VAO equal to Vd by 2, and I will give the gate pulses to S1 and S2. Okay, actually, but actually the current will flow through D1 and D2. Okay, because yeah, the devices will, the IGBTs will not conduct. Okay, so this is the case one. Similarly, if you take I less than 0, like here, the current is coming into this O terminal and we want a 0 voltage. Then if I give the pulse like S3 and D6, okay, so S3 and D6 will conduct. It will conduct like this. Okay, and similarly, if I is less than 0 and I want to get a minus Vd by 2, of course, I will then turn on S3 and S4. I will give the pulses to S3 and S4 and they will be turned on and the current will flow like this. Okay, so therefore, what we have seen is that if we have to get, so one thing that becomes obvious here is that if we want to give positive voltages like Vd by 2, I will give the pulses to S1 and S2. Okay. If I want to get minus Vd by 2, I will give pulses to S3 and S4. Okay. So this becomes very obvious. But for the zero state, okay, for the zero state, what I will do is actually I will give pulses to S2 and S3. Okay, I'll give pulses to S2 and S3 for the zero state. Okay, and what will happen is if the current is greater than 0, then D5 and S2 will conduct. And if I current is less than 0, then S3 and D6 will conduct. Okay, so the current will decide which devices out of S2 and S3 will conduct. Okay, but I will, so for this condition, for if I want to get 0 voltage, okay, at the output, I will give pulses to S2 and S3 simultaneously, and one of them will conduct depending on the direction of the current. Okay, so with this logic, we can actually come to the point where we can say that So therefore, we can say that for Vd by 2, we give pulses to S1 and S2. For 0, give gate pulses to S2 and S3. And minus Vd by 2, we give gate pulses to S3 and S4. Okay. So if we follow this way, we can actually find or we can actually get this kind of a 3 level. So this is the VAO voltage waveform. That is what it looks like. It is 0 sometimes it is Vd by 2, and sometimes it is minus Vd by 2. And this will actually emulate or try to replicate the sine wave which is inside this waveform. The fundamental component in this PWM waveform is what we are trying to replicate, right? Now, if you look into this one and think a little bit, you will find that this you will find that this thing here, uh, this logic comes out. Okay, S1 must be equal to S3 prime. So which means S1 and S3 prime, this one, and these two, S2 and S4, they will become complementary to each other. Okay, so this is what will happen. Okay, in this converter. You can also refer to the previous lecture in NPTEL from my course, and there I have talked a little bit more in details. But here we will, yeah. So here you can see that S1 and S3 and S2 and S4, they are complementary. Okay. One of the things that we must keep in mind is that it is possible to go from plus Vd by 2 to minus Vd by 2 directly. Okay, so for example, when you are operating this converter, you can as well go from this kind of a waveform also, which is typical for a two-level waveform. Okay, so this is a two-level waveform. Okay, but we do not go here. Okay, because of course it will increase the instantaneous error and it will cause a high dV by dt. So when we switch the three-level NPC, we do not go from plus to minus or minus to plus. Okay, we always go from plus Vd by 2 to 0, or we go from 0 to minus Vd by 2. Direct transition from plus voltage to minus voltage is avoided in NPC. Especially this is true because in many of these applications, we are talking about high voltages, high DC links, and going from plus to minus causes a huge dVdt. Okay, and so this will be very detrimental to many applications. Also in terms of generating noise in the system. So therefore, we actually avoid this one, and we will always go from plus to 0 or 0 to minus and vice versa. Okay, like what I have shown it in this diagram. Now, after studying the little bit of the circuit diagram, we can now say that, well, just like a two-level VSC, we have been able to actually, so this is the VSC here, which is connected to the grid. Okay, and this VSC, instead of a two-level, now we have a three-level. Okay, three-level VSC. And therefore, what we can also have seen in the previous slides, that this entire VSC, just like a two-level converter, can be again represented by a controllable AC voltage source, right? So this means that the analysis, okay, the power analysis and steady state current voltage that will be flowing through this, all can be exactly analyzed. Okay, because then the three-level NPC is considered as a controllable voltage source. Okay, so if you can change the magnitude, angle, and frequency of this VAN, VBN, VCN, you can allow a certain amount of P and Q to flow in this system. Of course, since it is a rectifier, so we will say that we will, if it is a pure rectifier, right, then we will say that we will not allow Q to flow, and we will only have the P to flow here, okay, from the grid and to the converter. Okay, so you can just have a look into some of the previous week's lectures on the two-level voltage source converter. This is an extension of that concept. Now, let us talk a little bit about the space vectors. Okay. Now, in the space vectors, if you remember that we had defined space vectors as something like this. So, load phase voltage. So, we take the three phase voltages VN, VBN, and VCN, and we multiply this like this. Okay. For a two-level converter with a 100 combination, what we got that VRT was 2/3 VD at an angle of 0 degree. So this was what the space vector diagram for a two-level converter looks like. Okay. So we have these 6 vectors, active vectors, and 2 zero vectors. Now, how does the space vector diagram for a three-level converter looks like? Actually, it looks like something like this. Okay. Now, remember, in a two-level converter, we have 3 phases and we had 2 levels of the output voltages. So the total number of possibilities, total number of switching states were 2 to the power 3, right? Now, in case of a three-level converter, again, we have 3 phases and 3 levels, okay, in each phases, right? So we can have actually, so sorry, this should be so not 3 phases. So in case of a two-level converter, we had 2 levels of voltages at the pole, and so therefore we will have for 3 phases 2 to the power 3. Similarly, in a 3-level converter, we have 3 levels in each phase, so we will have 3 to the power 3, which will be equal to 27 switching states, right? And these 27 switching states form what is called the space vector diagram of the three-level NPC. Okay, so for each of these switching states, we can now find out what is the space vector. Let us let us take one example here. Okay, suppose you have one switching state combination which is 0 plus 0. Okay, what does this mean? That in A phase, this is A phase. A phase, the voltage is 0. B phase, the voltage is plus Vd by 2. And C phase, the voltage is 0. Okay, so which means in A phase, the switches are the pole voltage is connected to the midpoint of the capacitor in A and C phases, whereas in B phase, it is connected to the top. So suppose, so therefore for 0 plus 0, VAO is 0 voltage, VBO is equal to plus VD by 2 voltage, and VCO equal to 0 voltage. So how will the instantaneous phase voltages, load phase voltages will look like? You see here, it is 2/3. We have seen this formula before. I'm just writing it down. VAN equal to 2/3 VAO minus 1/3 VBO and minus 1/3 VCO, which will be minus 1 by 6 VD. Similarly, VBN equal to 1/3 VD and VCN equal to minus 1 by 6 VD. So therefore, if you put into this formula of VRT, you find that this is equal to 1/3 VD at an angle of 2 pi by 3. Okay. So the resultant space vector, so this is called a small vector. Okay. We'll see what is small vector, what is large vector, what is medium vector. But this is what is the resultant here. So this resultant, you can see here, this is the resultant here, VA equal to VD by 3, right? Uh, you can also, instead of doing this mathematics, you can also do it graphically, assuming that you have this A phase here. So on this is a 0 plus 0. So which means on the A axis, you do not have any contribution. On the B axis, you have this condition because you are plus in B. Okay. And in C phase also there is no contribution. So you will get directly to this point. Okay, I will take another combination and I will show you. Okay, suppose this one minus 0 minus. Okay, so how can you do this graphically? So on A phase you have minus, so A phase is something like this here. Okay, and B phase is 0, so we do not go move anywhere in B phase. On the C phase you have this as the minus here. So if you do the vector addition of these two, we come to this point here. Okay, so therefore uh, minus 0 minus also produces this kind of a 1/3 VD at an angle 2 pi by 3. Okay, so the resultant vector for 0 plus 0 and 0 minus, sorry, minus 0 minus is same. In fact, if you go on tabulating all the 3-level NPC switching states, okay, there are 27 switching states. If you go on tabulating, so these are the possible switching states. Okay, you can see here all the switching states I have drawn. You will get a corresponding space vector. Okay, and these space vectors are basically what is creating this space vector diagram. Okay, here in this space vector, these blue ones, these are the small ones, small space vectors. There are these red ones, which are called the medium vectors, and then there are the black ones, which are called the large vector. Of course, you have zero vectors as well. There will be 3 zero vectors, because these 3 zero vectors will come from this 3 combination, which does not produce any voltage. Okay, so 3-level space vector diagram will have 27 switching states, which will be distributed over 2 hexagons. One is an outer hexagon like this, and one is the inner hexagon. Okay, um, and so you will be able to get this all the switching states mapped into this space vector diagram, right? So here, yeah, I have now we are showing it in a separate slide, that these are the small vectors. So all these combinations, so you can see all these combinations, we have these small vectors. Okay, and the small vectors will all the small vectors 1, 2, 3, 4, 5, 6. There are 6 small vectors, and all of them have a magnitude of 1/3 and an angle of 0, 60, 120, like that. But all of them have 2 multiplicities. You can see here, this is the multiplicity concept. Okay, means that these 2 switching states, both of them produce an identical space vector which have a small magnitude. Okay, so all small vectors have 2 multiplicities. All right. Uh, in a similar way, if you see this particular switching combination plus 0 minus, so here what will happen? Plus 0 minus means on the A phase you have given plus, so VAO is VD by 2. On the B phase you do not have any contribution, whereas on the C phase you have a minus VD by 2 combination contribution. So C phase is minus VD by 2. If you do the vector addition, you basically get this vector here, VR, 1 by root 3. Okay, remember we have, when we define this space vector, we have used a 2 by 3 factor at the um, at the beginning. Okay, so there is a 2 by 3 here. Okay, that you should keep in mind while doing the vector addition and finding out the magnitude, right? So therefore, VR is equal to 1 by root 3 times VD. So similarly, so here you can see that this plus 0 minus is creating a space vector having VD by root 3 magnitude at an angle of 30 degree. Here this angle is 30 degree. Note that this space vector, this length is 2 by 3 VD. Okay, this is 2 by 3 VD. Okay, this length of the hexagon. Okay, so so for this combination of plus 0 minus, we get what is called as the medium vectors. Okay, and so there are 6 more switching combinations which are written here now. all these will produce you the medium vectors. Okay. And similarly, if you take these combinations, okay, and there are 6 such combinations here, okay, these will produce what is called as the large vector. So if you take this one, A phase is plus, so A phase is plus, and B and C phases are minus here, okay, and then you can do a vector addition, and you will find that all of them are having actually this. We are now at the boundary or the corners of the hexagon, okay. And so, therefore, this will make these 6 combinations will make these 6 space vectors, right? So here now we have actually, okay, there is some problem in how the slides are getting displayed. There is some problem in this, but when you see the PPT, it will become correct. Okay, some problem in there in the slide one. Um, so please check the PPT. Okay, please check and so these ones it will come in the when we share the slides, it will come correctly there. Some problem here. Okay, so if you see here, therefore there are the whole space vector diagram are divided into large vectors, medium vectors, and small vectors, and zero vectors. Okay, so there are 12. So there are 6 small vectors and there are 12 switching states. Okay, so there are total 12 switching states here. So there are 12 switching states, and for medium vectors you have 6 switching states, and for the large vector also you have 6 switching states. And of course, you have 3 switching states for the zero vector. So if you add all of them, 6 plus 6 plus 12 plus 3, you get 27 switching states. And this is what are the possibilities. There are 27 switching states possible for this converter. And so we get all the. Now, for the space vectors, if you see here, these 6 switching states produce 6 large vectors. These 6 switching states produce 6 medium vectors. These 12 switching states produce 6 small vectors. Each small vector has 2 multiplicities. And of course, at the end, you have 3 switching states producing 0 vectors. And yeah, this is what we have noted here. Okay, 6 large vectors, 6 medium vectors, and 0 vectors. Now, once we have understood what is the space vector diagram and all, we can as well then start looking into the space vector PWM of NPC. Okay, and so basically the idea here is that if this is the reference vector is coming from the controller. Okay, the controller will dictate how much is the fundamental component of the voltage which is coming out of the neutral point clamp converter. Okay, it is exactly the same concept as the 2-level VSC which we have earlier seen. Uh, like we want to control the voltage output of the voltage source converter, whether it is a 2-level converter or it is a 3-level converter. We will exactly position this uh, voltage output so that adequate active or deactive power is exchanged with the grid. And so when this VREF is basically corresponding to the fundamental output voltage from the NPC. Okay, suppose this VREF is, now the question is, if the VREF is here in this, so we are now mapping that VREF into the space vector diagram. So if the VREF is in this place, how do we switch the different switching states? Because there are so many switching states. Okay, whom to choose and how to switch, for what duration this switching state has to be switched. All these questions have to be properly answered. Okay, so in order to do that, we first observe that, of course, one of the things that we should observe is that when the vref is here, okay, when the tip of the reference vector is here, we must switch the three nearest vectors, okay, available to us. As we have earlier told, this will reduce the instantaneous error to the minimum, okay. We can as well switch the outside vectors like these ones, but it will increase the instantaneous error, okay. So when the reference vector is here, we will always switch the three nearest vectors which are forming a triangle, and this reference vector is inside that triangle, okay. So this is now the question is, so if you switch this one, so suppose you go clockwise or anti-clockwise, like the two-level VSC, okay, how will you switch it? So suppose if you do it like this way, then what will happen here is you can switch it like this way. You see plus 0, 0, okay, plus 0, 0 and plus 0 minus. So plus 0 minus. So it starts from switching here, goes to here, then plus minus minus, plus minus minus, and 0 minus minus. Okay, this is how it is clockwise switching. At each point, you can see here, there's only one switching. So from 0, this went to minus. And from here, this 0 went to minus. And then from this plus went to 0. Okay, so this is how the switching can take place if you do go clockwise. If you go anti-clockwise, the reverse thing will happen. And so you suppose you start from 0 minus minus. So you start from 0 minus minus, right? And you then go to plus minus minus, and then you go here, and then you go here. Okay, so this is how the anti-clockwise will operate. So generally what happens is in one switching cycle, you once go clockwise and once you go anti-clockwise to come back. Okay, so it can be like this way. So we'll talk about it. This T0 by 2 and T1, T2, this one. Okay, or you can see the other lecture in YouTube where this has been taught in much more details. Okay, now a little bit of how do you actually get the timing duration and dwell time calculations. Okay, here you can see that the starting and ending vectors are not zero magnitude vectors. This is very important. Okay, so you can see here that we are going to start from this vector. Okay, but the starting and ending vectors, but this vector OB is not of zero magnitude. Okay, it has a certain magnitude. So let us take an example. Okay, so suppose you want to generate this OP. Okay, VREF is, so it will take like 0.45 VD at an angle 50 degree. Okay, it's just an example. So we are going to switch OB vector for T0 time, which will be split into these two, T0 by 2 and T0 by 2. And OA vector is T1, which is plus plus minus, and OC is plus 0 minus. Okay, and of course we have this condition TS equal to T0 plus T1 plus T2. So then, okay, this is not, this is not thing. So this is like VREF into TS is equal to OB plus OB into T0 plus OA into the plus OC into T2. Okay, so VREF at an angle VREF TS is 0.45 at an angle 50 degree. This is equal to OB. The OB length is how much? VD by 3. Remember, this is 2 VD by 3, right? And so this is VD by 3. So there is some problem with the slide. Anyway, so VD by 3 at an angle 60 degree. OB is VD by 3 at an angle 60 degree and times this T0 plus OA. OA is 2 VD by 3 at an angle of 60 degree. Here OA, and plus what is OC? OC is equal to VD by root 3 at an angle of 30 degree. This point OC. Okay. So you have got this one. So therefore, you can always find out the real and imaginary component of this equation. Okay, this is what 2 and 3 will tell us. Okay, and so this one will be something like this. Okay, so if you solve these 2 and 3 equations, what you will get is T1 equal to 0.919 TS, T2 0.27, and T0 as 0.454 TS. So which means that OP vector is closer to OB. Okay, there is some problem here. T0 is maximum. So T1 is yeah. So T0 is maximum. So OP vector is closer to OB. Okay. So it has also the same distance from OA and OC. So so this one for this OP vector we have OB. These three vectors are being switched and their durations are total T0 is 0.5. So about 50% of the time we are standing at the OB vector. Okay, almost more than 50%. We are standing in OB, and the rest is so OA vector is here. We are switching OA vector, and here we are switching OC vector. Okay, OA for T1 duration, uh, OC for T2 duration, and OB for T0 duration. Okay. And remember that OA is nothing but plus, minus, plus, plus, minus, and OC is plus 0, minus, and OB is plus, plus 0, and 0, 0, minus. Okay, so this is how this whole switching will happen. Okay, now, so remember always that what are the starting and ending vector? The small vectors with two multiplicities, these will be the starting and ending vectors for any switching sequence. So basically it means that this vector OB, okay, in this particular switching will be the pivot vector. Okay, this will be the start and end vectors, which are called the small vectors are the pivot vectors. Okay, so OB is this vector, so it is the pivot vector. So T0 will be split into these two. So you can see here what is happening. OB, which is equal to T0 by 2 duration, will have this plus plus 0. Okay, plus plus 0. Then OA will be switched, okay, for T1 duration, and then it will be plus plus minus, and OC will be then switched plus 0, minus, and then ending will be again at OB vector having a duration of time duration of T0 by 2, and it will be 0, 0, minus. Okay, so this this OB is now called this is the small vector, which is the pivot vector, because the starting and ending of the switching happens on the pivot vector. Okay, so generally what we do is we have the starting and ending vectors, okay, split into T0 by 2 and T0 by 2. Okay, it gives the best harmonic performance, but other types are also possible. And yeah, you can refer to some of the literatures on how these other types are possible. So in any switching sequence, therefore, is that we understand that this will be the pivot vector. So as long as you switch in this one, so this is the pivot vector. When you when you start using this vector, this will be the pivot vector. When you start using this vector, this will be the pivot, and this again will be the pivot, like this one. Okay, so therefore, with these pivot vectors as the starting and ending vectors, this three-level NPC will become just like a conventional two-level space vector diagram. Why? because if this is the starting and ending vectors, then we will think that this is the hexagon, okay, on which the switching will happen. So therefore, the three-level space vector diagram is an extension of the two-level space vector diagram. Okay, so you can see here. So you can also see this lecture. Okay, I have talked about it in details here. So every 60 degree, so these are the boundaries for the pivot vectors. The pivot vector changes. Okay, yeah, this boundary actually helps in the selection of the two-level space vector diagram. There are basically six sets of hexagons. Here there is one, then there is another one here. Okay, and then there is this hexagon here. Okay, all this has been detailed analyzed here. Okay, you can see these slides here. Okay, now one of the things is we have understood the space vectors and the diagram. When we go for the PWM for this neutral point converter, we we can use a carrier based PWM. So we can use a sinusoidal PWM. We can also use space vector PWM. I will not talk about space vector PWM in this lecture. But let us understand how sinusoidal PWM can be implemented, for example, for grid-connected applications. So here we basically used two carriers. Okay, there is a top carrier and there is a bottom carrier. Okay, carrier 1 and carrier 2. Okay, so what is the switching logic? The switching logic is if VREF, suppose you take any reference, if VREF is greater than 0, which means we are in the top side. So if VREF is greater than triangle 1, so what is triangle 1? This is triangle 1. Okay, and this is triangle 2. So if VREF is greater than triangle 1, then you turn on these switches. So we give the gate pulses S1, S2, S3, S4 like this one. Else, therefore, S1 is 0, S2 is 1. So basically we are switching the middle two switches, and S1 0 and S4 of course will be 0, because here we are going to switch between 0 and VD. This is what our target, 0 and VD plus VD by 2. Else, if VREF is less than 0, that is we are now in this part, okay, for A phase. Then if VREF is greater than triangle 2, then we switch on this one so as to get minus, so as to get 0. And if we switch this one, we get minus VD by 2. Okay, so this is how the switching is used. Okay, when you use the three-level neutral point clamp converter, and this will typically for an A phase will give an output like this, 0 and VD by 2 and minus VD by 2. Okay, this is how the sinusoidal PWM works, right? And suppose if you then put it into practice, and you can show some of the waveforms. Here you can see this VAO voltage plus 300 to minus 300. I have taken a DC link of 600 volt. Okay, and suppose I have taken 2.25 kilohertz as the triangle frequency, which is 45 times the fundamental. So here you can see 3 levels in pole voltage and 5 levels in line voltage. VAO, VBO, VCO, there are 3 levels. Okay, this is the 300 level, this is the 300 level, this is 0 level, and this is minus 300 level. And therefore, of course, VAB has 5 levels in the pole voltage, line voltage. And the load phase voltages and currents are also shown here. Now, if you see the harmonic spectrum of the pole voltage, where will you see the first band exists around 2.25 kilohertz. Okay, and yeah, so if the modulation index is 0.98, the peak voltage is here, okay, 294 volt. That is where it will come. Okay, now one of the things that you should note here is that the switching frequency of the switches, okay, is 23 times, is half of the carrier frequency. Okay, how do you see this is 23 times? You can calculate from here, okay, starting from here, okay, or from here, okay. Suppose you take the top switch, then you will see this 1, 2, 3, 4. You can go on calculating like this. You'll come out to be 23, 23 switchings here. Okay, so which is basically 2.25 kilohertz. This 2.25 kilohertz was about divided by 50, which was around 2250 was around 45 hertz, 45 times. Okay, this was 45 times. So basically, the switching is happening at 23 times. So the first band of harmonic frequencies are at twice the switching frequency of individual switches. Okay, this is what will happen here. We can also implement space vector PWM, okay, using a single carrier strategy. So we add the first offset to the reference wave, like in space vector PWM in a two-level converter. And in the second stage, we add a second offset, okay, so as to make the starting and ending vectors of equal duration. So we will not cover this in this lecture, and you are referred to this particular lecture so as to get an idea about how space vector PWM is implemented. So we stopped here.